Welcome back to Physics 141. Last time we spent quite a bit of time defining work and then explaining how to calculate it for different situations. In some cases, the force that was acting on the object was constant. In some cases, it was changing. And in some cases, the object was moving along a straight line path, and in other cases, along a path that had components along x, y, and z. But we didn't answer the question, why bother doing all this? What is it worth to define and calculate the work done on an object? Well, let's consider the work done on an object that's experiencing a constant force and moving in one dimension. So the net work is equal to the net force times the displacement delta x, according to the definition of work. And because now we're talking about the net work and the net force, it means the work done by all the forces. And so because of that, because this F net represents the sum of all the forces, we can replace it with mass times acceleration according to Newton's second law. And because we're dealing with a constant force, we know that it has a constant acceleration. So we can now go back to one of our kinematic equations for constant acceleration motion and express the acceleration in terms of the initial and the final speed using this familiar equation. So solving for A gives us v squared minus v0 squared over 2 delta x. And we can take this and plug it into the expression above for the net work. And when we do that, we see that we get m times this quantity v squared minus v0 squared over 2 delta x times delta x. So the delta x displacement term cancels, and if we take the 2 and bring it outside as a 1/2, and we multiply through the m, we see that we've got 1/2 mv squared minus 1/2 mv0 squared. So the net work is equal to the difference between something that depends on the mass and the initial speed, the final speed, and something that depends on the mass and the initial speed. And usually, instead of using just v and v0, we make it explicit which one is which by writing this expression as 1/2 mv final squared minus 1/2 mv initial squared. And this is a statement of what's known as the work kinetic energy theorem, or just the work energy theorem. So let me see if I can get back to that. Okay, so that's the main result in this section. And because this term 1/2 mv squared appears both for a final and for initial situation, we define that to mean something significant. We define the kinetic energy, and we'll call it just K. Some books use KE, but K is fine here. We'll just define that to be 1/2 mv squared, so that if we understand that definition, the net work done is just the change in the object's kinetic energy. And if you've never heard of it before, kinetic refers to motion, so that kinetic energy is the energy associated with the motion of an object. It's not all of the energy, but it is the energy associated with motion, and the fact that it depends on v makes that clear. So, because of our ability now to calculate the work done on an object by all the forces, we can use that information, and if, let's say, we know the initial velocity, we can then calculate the final velocity. And so this forms the basis for using so-called energy methods to solve problems in mechanics. And we will do that. We're making the transition from solving problems using Newton's laws to solving problems in this supplementary way using energy methods. Here's an example. A block with a given mass is initially at rest at position x equals 0 on a horizontal surface. It's acted upon by a net force that's shown in the graph here. So we want to find the final speed when the block reaches x equals 4 meters. So x equals 4 is right here. And what we need to do then is find the net work done on the object starting at x equals 0 all the way up to x equals 4. And then that will allow us to calculate the final speed because we know the initial speed is 0. So this is a pretty easy problem. We have to remember that the work done, if you have a force versus position graph, and the force here is changing, the work done is the area underneath the force position graph. So what we need to do, in addition to using the work energy theorem. And here you can see that since the object starts at rest, the V initial term is 0. So the net work is just 1/2 mv final squared. So we'll use this, but then we also have to remember how to calculate the area underneath the curve. And once we can do that, this equation shows how we will find the final velocity, the final speed. So the net work on the object as it moves from x equals 0 to x equals 4 would be the work done from 0 to 2. And it's helpful to break the net work up into 3 pieces because we've got 3 straight line segments in the force graph. So 0 to 2, 2 to 3, which is when we have this downward sloping segment, and then 3 to 4, which is the final location of the object. So those are easy to write down. The work done from 0 to 2, well, that's just the area of the rectangle that has base 2 and height 2, so it's 4 joules. And then from x equals 2 to 3, we have a segment that goes from being positive to negative, and it's symmetrical because it passes through the x-axis at 2.5. So the positive area between 2 and 2.5 is exactly equal and opposite to the negative area between 2.5 and 3. And so a little inspection will show us that the work done between 2 and 3 is 0. And finally, 3 to 4, that forms another rectangle that has a base of 1 and a height of 2, only it's negative because the force now is in the negative direction, which opposes the motion of the object. So this object started off with a positive force, and then somewhere along the way the force changed direction and began to slow it down, but not quite to stop it. So the work done from 3 to 4 is negative 2 joules, so 4 minus 2 is 2 joules. The net work is 2 joules, and it's important that it be positive. So that term then can be plugged into our equation, and then we substitute for the mass. So the final velocity is 2 over 12 kilograms times 2 in joules. I'm going to put the units in. A joule is a kilogram meter squared per second squared. So under the square root, the kilograms cancel, leaving meters squared per second squared, which when you take the square root gives you meters per second. So our final speed is 0.58 meters per second. And that's a simple example of how we can use the work energy theorem to solve for the change in the motion of an object when we know the force. Now, one more topic that I'd like to talk about today in connection with work, and that is power. And power, the definition of it, is the rate at which work is done, or the work done per unit time. So if there's 2 people that are each doing the same amount of work, but one can do it faster than the other one, then we say that that person exerts more power. So let's make that definition clear. Power then is the change in work with respect to time, and so we write it here in this derivative form, but often we will sometimes just write this as delta W over delta T when we do the calculation. So the unit of power, if the work is measured in joules, then power is in joules per second, and that's easy to see, but it's also given its own name, which is the watt, named after James Watt, the inventor of the steam engine back in the 1700s. So I want to do a quick example using power, and just to preface the example, I'll say that large amounts of electrical energy are often consumed, and we consume them on a monthly basis in our homes, in residence halls, and quite often those large amounts of electrical energy are generated over short times, like, for example, a couple of hours. And because of that, we often quote power values in kilowatts, even though watt is the standard unit. Instead of having 10 to the 3 or 10 to the 4 watts, we'll talk about 10 kilowatts or 1 kilowatt. And so as a result, we sometimes quote work or energy values, rather than saying that they're in joules, we'll quote them in kilowatt hours, which is a non-standard unit, but it is used often by utility companies in measuring the usage of energy by their customers. So here's an example. How many joules of energy are required to run an appliance that has on a label information that tells us that it draws 1.5 kilowatts? So it's a 1.5 kilowatt appliance, and we want to know how many joules are needed to run that thing for 24 hours. Maybe it's a light bulb, maybe it's a radio, something like that that you have that's on for 24 hours. So how do we do this? Well, we go back to the definition of power, and assuming that the power is constant, that it doesn't change over time, then we'll take this definition up here and just write it down then as power equals the change in work, or the amount of work done divided by the amount of time. And here we're trying to find out how many joules of energy, and that means we're asking how much work is done. So solving in this equation for the work term, we get delta W is P delta T. So we can calculate the amount of joules of work done by writing down that we have 1.5 kilowatts times 24 hours, right? And remember, the kilowatt is a power unit, and so it's actually, kilowatt is a measure of energy per time, so we multiply by time, and we see that that gives us an energy rating of 36 kilowatt hours that are being used. And if we wanted to change that to joules, because it is a non-standard unit, we would need to multiply by a couple of conversion factors. And remember, a kilowatt, kilo means 10 to the 3, so 1 kilowatt is 10 to the 3 joules per second. So we multiply by that conversion factor, which will get rid of the kilowatts and replace them with joules. And then our hours need to be converted into seconds, so we multiply by 3,600 seconds per hour. And when we do that, we get this huge work amount, which is 1.3 times 10 to the 8th joules. So you can see now why kilowatt hours, 36 kilowatt hours, is a much more convenient figure to work with than to talk about 1.3 times 10 to the 8th joules. So on your utility bill, you won't see ratings in joules, you'll see kilowatt hours. Went through this already. Must have had a duplicate slide. Okay, one last thing then. There is another way of expressing the equation for power in terms of the motion of an object. So to see how this arises, just remember that work is essentially force times displacement. So if a constant force is used, then the power, or the rate of work done, should depend on the rate of displacement. So think for a second. What's another way of describing the rate of displacement? The amount of displacement of an object per unit time. So if you move from point A to point B, you go through a displacement, and that displacement divided by time is just your velocity, right? So in one dimension, the work done is F sub x, delta x. It's the component of the force along the x direction times the displacement delta x. And so as a result then, we could calculate the average power for this work being done just by dividing by an amount of time, delta t, whatever time it takes to do the work. So that gives F sub x, delta x over delta t, and delta x over delta t is just the velocity along the x direction. So it's actually, more properly, it's the average velocity. But since we're calculating average power, then that's consistent. So the average power is the x component of the force times the average velocity for an object moving in one dimension. Instantaneous power would simply be the derivative, which can be expressed F sub x times the instantaneous velocity. Or, if the force is not along the same direction as the velocity, what we really need to use is the dot product, because then it allows us to find this power term for an arbitrary direction of the force and an arbitrary direction of the velocity vector. So those just close our discussion of power, and knowing now about work, what it means, how to calculate it, and what it's good for, how the amount of net work done on an object is related to the change in the object's velocity, now we're setting the stage for the development of the principle of conservation of energy. And that principle is a great problem-solving tool that we will exploit quite significantly in the weeks ahead. I'll see you in class.